Hi guys, my name is Avinash Kumar. Welcome back to my channel Stochastic Programming. So in this video, we will talk about locality sensitive hashing. Hashing in general is my personal favorite topic, and I was trying to create this video from last few weeks, but now finally I got this motivation as well. So last week we saw one of the massive hack on Twitter's account, and well, if you're not aware about that hack, I mean, I have provided link in the description so you can read more about it. So in general, I mean, as usual, the main intent behind this attack was to earn financial benefits in the form of Bitcoin. Which is why on July 17, Twitter was in news for one of the most high-profile security breaches in recent years. Attackers broke into Twitter's account of world leaders, celebrities, tech giants, and sends out tweets about offering $2,000 for every $1,000 sent to an anonymous Bitcoin address. Why this happens, who is behind that, well, we are not discussing here. So given a problem statement, let's say in future to prevent these type of attacks, Twitter wants to build system that is capable enough of detecting similar tweets and reject based on the similarity index. Well, at this point, you might have questions like why Twitter will try to build such system and why not they are improving their authentication system, why attackers got easy access on users account and so forth. Well, you're right, but we have to accept one thing that password-based authentication systems are not that much secure. They can be leaked through various attack channels, attack models. Well, there are plenty of ways by which attacker can find our passwords very easily. Another question you might have, like what if there is a legitimate reason and people are posting similar tweets across all over the Twitter and their accounts? With the presence of such system, no one will be able to post anything on Twitter. Well, that's a good question to ask, but let's consider the system is capable enough in differentiating normal and suspicious tweets. Now at this point, I believe you are pretty much convinced why we need to build such system. Well, maybe not. No worries. Let me give you another example. Let's think of an application which is producing unstructured data over cloud, let's say customers review or feedback system, which is responsible for collecting and storing all the customers review for respective product. Now to expand your business financially, your marketing team decides to address those reviews and improve product services and features. Now, one naive approach one can think is to read all those reviews manually, filter them, and get awareness about customers liking and disliking. Now, this is something which is, difficult to manage and scale, which is why you will go for a system that should be capable for searching similar documents based on your input search query. To understand locality sensitive hashing, let's understand what is hash. A hash is any function that can be used to map data of random size to fixed size values. The value written by a hash function is called hash values, hash code, message digest, or simply hash. A typical cryptographic hash function computes same hash for the same input. As you can see in the example, for two similar inputs, corresponding hash values are completely different. Which is why we cannot use normal cryptographic hash functions to build such system. This is where locality sensitive hashing comes in. So the basic idea is if you have documents which are similar to each other, maybe they can be different by some characters or maybe by words, but still you want to generate same hash codes. This is where this technique can help us to achieve that. And why we are actually computing those hash, because the thing is we cannot compare all the documents every time. So hash functions, as I mentioned, they are fixed size, so we can use them as key for our hash tables, and in the searching process the searching cost will be minimized. Let's consider the same example. We want to generate hash code in such a way that document B and C lands on the same hash value in the bucket. So the way LSH works is you take a space, you start cutting it with hyperplanes. Well, here hyperplane is nothing but a line that is used to partition our space. Randomly we refer one side as 0 while the other side will be 1. So the way it generates the hash code is by setting first bit as 0 for all the points which are present in the region below the hyperplane. Similarly, points which are present in the region above the hyperplane will get their first bit as 1, which means for point A, B and C, first bit is 0, while for the points D and E, their first bit is 1. We will repeat this process for the second hyperplane as well, and guess what? That second hyperplane will be responsible for assigning second bit of the hash code. Well, in this case, second bit for point B and C is 0, while for others it's 1. We will do the same process for the third hyperplane as well. Well, it's based on the requirement. We need to decide how many hyperplanes we need, but in this case I'm using 3 hyperplanes for this problem. So what we have done up till here is we have partitioned our space into disjoint regions. For each disjoint we have assigned either bit 0 or 1. Based on that, we have compute hash codes for each documents in the space. In short, for point A, the hash code is 010. Why? Because it lies on the 0 side of the orange hyperplane. Similarly, with respect to blue hyperplane, it is located on the side marked with bit 1. And obviously with respect to brown hyperplane, it is located on the side which is marked with 0. So after computing hash codes for all the points which are available in this space, we can see our duplicates. Here in our case, B and C have generated same hash code, so as D and E. Now if you look closely, B and C are same, which is good because we have found our first duplicate documents. However, in case of D and E, we have got false positive. They are far from each other, but because of our position of the hyperplanes we end up having the same hash code. Well, this is actually depending upon how many hyperplanes you are using. But this is not an issue because LSH is an iterative algorithm. We will not gonna stop here. In the next stage, we will repeat exactly same sequence of steps, and as we can see in the next iteration, when we perform exactly same steps, due to the position of our hyperplanes, this time we compute different hash codes for D and E. Now you might have this question, when do we will stop and get all our duplicates? So the way it works is we will run our algorithm for the fixed number of times. Let's say it's 25, which means we will get 25 hash tables. We will look for duplicates for all the 25 cases. Now the thing is, as I mentioned, there can be chances that you'll get some false positive, which is fine in the sense that let's consider that you want to search all the negative reviews in your review system, and you are getting some false positive, which is fine. When you will address those reviews, you will not gonna read, but the number of false positives should not be more, otherwise it will be again a manual process, right? But this algorithm actually performs better in these type of situation, and it doesn't give oftentimes false positive. But again, there can be chances that after running fixed number of times you won't get any duplicates, because as I mentioned, this is a probabilistic algorithm. You will get approximate results, not the definitive answer, right? And I believe this is why when we type any query on Google search engine, sometimes results on other pages are not that much relevant. This gives an impression of false positive in a search engine like Google as well.